Dear students and participants of the course on railway engineering, we are back with our discussion on the railway engineering parts and various modules. Today we are going to further discuss on resistances. In the previous lecture, we started our discussion on traction. We talked about the electric traction and the diesel traction and the locomotives. We discussed about the various comparisons with respect to those two locomotives, and then we shifted to the resistances which are being offered by the track or by the rolling stock, and there we talked about the rolling stock resistances which can be independent of speed, dependent on speed, or atmospheric conditions can be there. And in the case of track profile, where the two types of resistances may be offered, one is by gradient, another is by curvature, we completed the gradient resistance. In today's discussion, we will be following further and we will be starting with the resistance due to curvature. Then we will be talking about the resistance due to the start of the train or due to acceleration. And then finally, we will be taking the effect of wind as a part of our resistances which are offered to the movement of a locomotive or a train. So, let us start with the resistance due to curvature. Now, when we are talking about this resistance due to curvature, we have already discussed certain things when we were talking about the coning of wheels. So, there is a sleeper, there at the top of that there are rails, and then at the top of rails there are wheels and axles which are moving. When this is happening and there is a curved section and the train starts moving on this, then the centrifugal force starts acting outwards, which shifts these wheels towards the outer rail, and that creates more diameter movement on the outer rail as compared to the inner rail. So, this is a rigid frame, and due to that particular rigid frame, this type of a situation will arise. So, if we talk about the rigidity of the wheelbase and the movement of the wheel is on rails, and this is going to be different because of the curvature, because on the outer side the distance covered is more. Whereas, if we talk about the inner side, the distance will be lesser, that we already discussed with respect to the diameter of the wheel. The flange, another thing is, when this lateral shift is there, then the flange will be hitting the rail head and the side of the rail head. So, the flange of the outer wheel of the leading axle rubs against the inner side of the outer rail, and flange of the inner wheel on the trailing axle rubs against the inner side of the inner rail, because now when you are talking about the overall bogie and it has the wheels. So, there is a wheel here and this again wheel is here. So, this is an axle, but then it is being connected with another axle. Say this is a front axle and this is a rear axle, and you are moving in this direction. So, when you move in this direction, what will happen? Now, you are trying to negotiate with respect to these wheels on the rails, and because the force is acting, this force has taken it outwards, but the shift will come here because of this rigidity, and this will move to inner side. And when it moves to the inner side, and that is the reason why the trailing axle is rubbing against the inner side of the inner rail. And these two conditions, one appearing on the front axle, another appearing on the rear axle, is going to create the wear or is going to create the resistances. Another thing is the gaps which gets created between the inner wheel on the leading axle and the inner rail, and between the outer wheel on the trailing axle, which tends the train to derail if those gaps are higher. Here you can see the gap is being provided, but say if the widening of the gauge happens and this rail has shifted either to this side or this rail has shifted a bit towards the outer side, then what will happen? Already some gap was given, some more gap has come up, there is always a possibility of a derailment. So, that is also another issue which needs to be taken into consideration, and that is where the resistance is being talked due to the curvature. So, this was going to be induced because of these reasons. The reasons which we also talked in terms of the coning of wheels, there also we said there is a longitudinal slip, and this longitudinal slip causes when the forward motion of the wheels on a curved track are there, then this longitudinal slip is going to be there. If the wheelbase is long and the curve is sharp, then the condition worsens further. Another thing is there can be a transverse slip also, and this transverse slips increases the friction between the flange and the rail interaction. Then provision of insufficient super elevation, because you are talking about a curve, so the outer side has to be raised with respect to the inner side. And if this is insufficient, then in that case there is going to be more pressure on the outer wheels. And again, the interaction between the flange and the rail head has increased, and it will increase the resistance. So, these are the values which will be taken into consideration, and all research has been done on this so as to arrive at the factor. Now, further, the provision of extra super elevation may also create a problem. Now, when it is an extra super elevation, we were supposed to provide this, but what we have provided is this one, then there is a transverse slip which will take place, and on the inner side there is going to be more interaction as compared to the outer side. So, the friction on the inner rail will be there. Apart from these things, the poor track maintenance, the worn out rails, improper levels of rails, these things will also increase the friction on the curved track. Now, when these frictions are there, now what are the values which are going to be there, how it has to be computed, that is what we are going to look at. So, here we have provided a section. So, this is a rail here and this is another rail at this point. Now, when the train is negotiating this curve and there is a centrifugal force acting outwards, the shift is going to be there towards the outer side, and that is where the diameter here increases and inside it decreases. So, it says the distance travelled on the outer wheel is d1 because of the higher diameter, and in the case of inner wheel it is d2 which is going to be lesser. So, and that is required also because when you talk here about the radius, that this radius is r, but when you reach this point then the radius is going to be r plus g. Okay, so that is the value which is going to be added. So, what is the extra distance which is being travelled? The extra distance which is travelled is d1 being higher. So, d1 minus d2 is the value which will be there. Now, if we talk that there is the force of sliding friction is there and it is going to work here. So, the total force which is work done which is going to be there is force into distance. Force is a sliding force F and the distance travelled extra is d1 minus d2. So, we have d1 minus d2 into F. Now, if we talk about the average condition here, so in the case of this average condition we have a distance travelled d. So, if we have this distance travelled d, the mean resistance which is going to be there is d1 minus d2 into F divided by d, and then this d1 minus d2 and d values they can further be correlated because this is a distance being travelled we are talking, and there is an angle at which this distance is coming up. So, if we talk about with respect to this angle, so going by the radius and the angles what we get is that it will come out to g into alpha into F divided by r into alpha, and finally it is F into g divided by r. So, this is the value mean resistance which will be coming up. Now, this resistance gets affected by the force of sliding friction, gauge of track and the degree of curvature. Now, this degree of curvature instead of writing r, now we are instead of radius we are talking here in terms of degree of curvature, and that is being denoted as dr. Considering these, the values of the curve resistance have been computed, and in the case of the broad gauge it is 0.0004 into W into dr, where dr is the degree of curvature, or we can say this as 0.04% of WDR. In the case of meter gauge 0.03% of WDR, and in the case of narrow gauge it is 0.02%. So, at the moment we are emphasizing on the broad gauge. So, this is the value which we are going to take forward. Now, some specific points with respect to these curve resistances. The curve resistance increases with the speed of the train. So, this is one point. The another one is the curve resistance is not affected by the length of the train, because it is going to be affected in the bogie form. So, whatever the bogies have been provided below the wagons, so that is there. So, that size of the wagon is not big. So, that is where the length is not going to make a difference here. It is less with new rails as compared to the old rails. Okay. Then under the normal good conditions it may be 0.2 kg per tons per degree of curve, and under the bad track conditions it may be as high as 1 kg per ton per degree of curve. So, once you have a tentative value which is available to us in the case of a new track or in the case of a old track. So, if it is an old track it says 1 kg per ton per degree of curve. So, if it is 2 degree curve, that means it will be 2 kg per ton, and if it is 1000 tons, then it is 2 into 1000, 2000 means 2 tons resistance is going to be there in this particular case. It depends upon the central angle of the curve also. Okay, so the central angle of the curve, so that is what we are looking at here. So, these are the points related to it. Now, let us look at one of the numerical here. There is a train which is weighing 1200 tons. So, this W is being provided to us and it moves on a broad gauge track with a gradient of 1 in 200 and a curve of radius 860 meter and length 1720 meters. Calculate the resistance due to gradient and curvature and both. Now, when you talk about the resistance due to gradient, we have discussed it was W into sin theta or W into tan theta, or we talked about it in terms of W into percent slope. So, going by that, W into tan theta, we have W 1200 tons and then the slope is being given as 1 in 200. So, if we use that, the resistance comes out to be 6 tons. In the case of a broad gauge track, it is 0.04% of W into dr. So, this 0.0004 into W into dr is the resistance which is going to be offered. When we put the values here, now for this dr, this is degree of curve, we have given data here, the curve, radius and the length. So, the curve, radius and the length if we use, so considering angle with respect to the length and radius. So, what we get is 1720 divided by 860, that will be the angle in radians which will be available, and that is being multiplied with the other two values, that is 0.0004 into 1200, what we get is 0.96 tons. Therefore, the resistance due to gradient and resistance due to curvature, it comes out to be 6.96 tons. So, this is the amount which will be there. Now, let us come to the resistance due to the tractive effort, and this resistance due to tracting effort is going to be caused due to the start of the locomotive and train as well as due to the acceleration given to the locomotive. So, train is on a standstill condition here. So, V is equals to 0 and then the locomotive starts hauling it in forward direction. So, it has to provide certain more force because there is an inertia condition where it is trying to remain there. So, this is one thing. So, it is starting the locomotive, it puts, so it has to put more pressure here. If this is the locomotive and it is starting going up, so more pressure has to be placed. Then only this pull is going to be there, and that is where this is creating some resistance. So, it will come in the form of a resistance. And another one is that it starts increasing the speed and it gives an acceleration. So, there again the same thing is going to be an issue. So, let us look at the resistance which is getting due to the starting of the train or the locomotive. As per the object, these are going to be different for combination of locomotives and trailing vehicles. If we talk, it is given as 0.15 into W1 plus 0.005 into W2. where W1 is the weight of the locomotive and W2 is the weight of the trailing vehicle in tons. That means whatever the number of wagons which have been attached to the locomotive, accordingly this weight will be there. So, we have looked at one of the numerical where it was given that there were certain AC coaches and the second sleeper coaches, and the weights of those coaches were known, and on the basis of that we computed it somewhere around 596 or 99 tons inclusive of the weight of the locomotive. So, if you remove the weight of the locomotive there, that is the WT which will be computed. And in terms of an acceleration, this is being defined because there is a change in the speed with respect to time. So, it is V2 minus V1, that is the change with respect to the time t, and it is given as 0.028 into W, that is the factor which is being attached to it, where V1 is the velocity at the beginning in kilometers per hour, V2 is the velocity at the end of the acceleration phase, T is the time taken in seconds to achieve the speed from V1 and V2, and W is the total weight of the train in tons. So, it includes total weight, means it includes both the wagons as well as the locomotive. So, this formula can be utilized here. If this is not being given, if the acceleration rate has been given, then the acceleration rate can also be utilized here. So, finally, the resistance due to the tractive effort comes out to be what? The resistance due to tractive effort comes out to be the starting of the train and the acceleration of the train. For the starting of the train, it is 0.15 into W1 plus 0.005 into W2, which was there, if you remember, point here. And in the case of the acceleration, it is 0.028 into W into the acceleration, that is V2 minus V1 divided by T. Now, let us look at numerical here. The train weighs 1200 tons. So, this is the total weight. Out of that, the weight of the locomotive is 110 tons. So, this is a small W1 or capital W1 if you want to write that way. The train moves on a broad gauge track at a speed of 100 kilometers per hour. So, V is given here. It attains this speed in 300 seconds. So, T is the time from a speed of 20 kilometers per hour. So, this is V1 and this is V2. Calculate the resistance due to tractive effort. So, resistance due to tractive effort is a combination of starting and acceleration. On the basis of that, this is the equation which comes out to be 0.15 into W1 plus 0.005 into W2 plus 0.028 into W into V2 minus V1 divided by T, and all of these information are available to us. So, when we put these information here, then what we get is, so W1 is the weight of the locomotive, so 110 tons is being placed here. W2 is the weight of the wagons which have been pulled, so the total weight is 1200 minus 110. So, what we get is 1090 is tons weight of those wagons. So, that is being used here, but at this point it is the total weight of the train. So, 1200 is being used and this is 100 minus 20 in 300 seconds. So, we get 16.5 as one value, 5.45 and another value, and 8.96 as the third value, and altogether it comes out to be 30.91 tons. So, a very big resistance is being offered because of this starting and acceleration condition. Now, there is a resistance due to wind. So, let us look at that. Now, this resistance due to wind, it is going to be dependent on what? It is going to be dependent on the intensity and the direction from which the wind is blowing. Say if we are moving in this direction, so this is the train movement direction and the wind is coming at some angle theta. So, it will have two components, one perpendicular to the direction of travel, another in the direction of travel, but working opposite in this particular case. If the wind has been in this form, then that wind component could have gone in the direction of the travel also. So, in that case it will work as a push, not as a resistance. Here when it is coming in the opposite direction, so this is working as a resistance. So, we have cos V cos theta as that form. So, the wind velocity, the sectional area, that is another thing, because how much of the area is being exposed? The whole of the train is exposed actually. So, whatever is that sectional area which will be there, the wind will affect on that. So, when V cos theta we are talking, so what the train is moving in this form and this is the sectional area which is going to be affected. Considering that, the formula which comes out to be for the resistance due to the wind is 0.000017 A into V square. That means there is a square effect of the speed in this case, and the sectional area A is being taken in meter square. So, if we have these values available to us, we can very easily calculate the resistance due to wind. So, what is the total resistance to traction? The total resistance to traction is going to be because of the track, because of the profiles, because of the starting and acceleration, and because of the wind. And when I put all of those together in terms of the formulas which we have seen so far and used, this is the bigger thing which comes up. So, we got formulas for the RT1, then we have, so the first set is for the RT1, the second set from here is for RT2, then the third set from here is for RSA condition, and then finally we have the wind resistance. So, if this is a situation which is happening and we have to calculate the resistances to the traction, then in that case what are the requirements of the data? The requirements of the data, if you look here, the W is required, so weight of the train is required. We require the speed at which the train is moving. We require the gradient at which the track is being provided. If the gradient is not there, then this W tan theta is not the contributing factor, it will become 0. We require the degree of curvature, but if it is a straight track, then this dr will not be there, it will become 0. We need to have a weight of the wagons as well as the weight of the locomotive separately other than the total weight of the train. We also require to know that what is the speed from where the train started accelerating at a higher rate, and what is the final speed which is achieved and how much time it has been achieved. So, that is the data which will be required again. And finally, if we are interested to look at the effect of the wind and the wind is blowing, in that case this cross sectional area will also be a one another data which should be available to us. Now, let us look at one of the numerical on the basis of this overall condition. Here it says the train is driven on a broad gauge track by a locomotive with an axle load of 28.42 tons and 4 pairs of driving axles. So, a bit different condition, 4 pairs of driving axles have been given and one axle load is 28.42, it means now the combination is 28.42 into 4. It is laid on a gradient of 1 in 100. So, the resistance due to gradient is there. When we have talked about this, then the resistance due to the track is going to be there. There is a curvature also being given as 3 degree, it means the resistance due to the track profile is there in terms of gradient and curvature. The total weight of the train including locomotive or wagons is given. So, this is total W. If we require to know separately the weight of locomotive and wagons, so some data is being given here. The speed of the train is given, so V is here. We have to calculate the resistance offered to the traction. If we talk about the overall system, then it is RT1 plus RT2 plus RSA plus RW, but there is nothing is being defined in terms of the wind effect. So, RW is not there, and if we talk about RSA, then this is also not being discussed. So, that part will also not be there, and that is where it has been struck out. So, we are left with only this much portion of our bigger formula to calculate the resistances. Now, what we need to do is we need to put in the information here. So, W1 is the weight of the locomotive and the weight of the locomotive has been given here, that is 28.42 into 4 pairs of driving axles, and it is being subtracted from 1640 tons will give you the W2 weight. So, and that is where total W is 1640, and the formula we have put the values all of those values here, and this is the weight of the locomotive, and 1640 minus the weight of the locomotive is being used in this way. Finally, altogether if we consider these resistances where we have not talked about the resistance due to the starting and acceleration, we have not talked about the resistance due to the wind effect, it still comes out to be 57.09 tons. So, this is a big value, and this big value is going to make an impact to the hauling capacity, as I said to you in the very starting. Let us look at one another example here. Now, there is a train which is driven on a broad gauge track by a locomotive with an axle load of 28.42 tons and 4 pairs of driving axles. So, that means again, as we discussed in the previous numerical, this is going to give us the weight of the locomotive W1. The track is let at a gradient of 1 in 250. So, we have a value with respect to the gradient. The curvature at a section is 2 degrees. So, we are being given dr here. Then the total weight of the train including locomotive wagon is 1240 tons. So, this is total W, and if we subtract from W1, what we will get is W2. So, that means W2 is W minus W1, which is possible. And then the speed of the train is given as 50 kilometers per hour. So, this is the speed. The train attains the speed of 50 kilometers per hour from a 10 kilometers per hour in a time of 300 seconds. That means we are being given as V2, V1 and T. The headwind impacts the locomotive having a sectional area as 12.5 meter square. So, the sectional area A is also being given. Now, we have to calculate the resistance offered to the traction. So, what you can see, more or less all of the conditions have been given here, and therefore, the formula which we are going to use is the complete formula so as to calculate the resistance to traction. So, when we put all these values here, so we have W as 1240, then we have speed as V and W as 1240 and V square. This is the gradient which is being used here. Then in the case of W1 and W2, we have the values being given here 113.68 and 1126.32 on the basis of the total load being given. The total W was 1240. So, this is the value which has computed from there, and then the speed differential in 300 seconds, sectional area affected by the wind speed. So, once we talk about these things, then what we get here is the total value comes out to be 42.6081 tons. So, this 42.6081 tons is the total resistance which is being offered to traction in this particular case. Now, the another thing which we can discuss is the compensated gradient for curvature. Now, when you are talking about this, what is happening is the track is being laid on the curvature with the radius r, but at the same time it is going up or down in some slope, say 1 in 200, 1 in 100, 1 in 50, whatever it is. So, two resistances are being offered, one resistance is Rg and another resistance is Rc, and when they both are coming together, then this will create a big problem to the locomotive hauling capacity. That is where what we need to do is we need to reduce, we need to compensate the gradient if the curvature is overlapping at that particular point. And what is this rate of compensation? This rate of compensation is, in the case of broad gauge, 0.04% for every 1 degree of the curve. That means if it is a 2 degree curve being provided, then it is going to be 0.04 into 2, so 0.08%. In the case of meter gauge, 0.03%, in the case of narrow gauge, it is 0.02% for every 1 degree of the curve. So, these are the values which will be considered. Now, let us look at a numerical with respect to this. We have to calculate the compensated gradient on a broad gauge track. So, when it says it is a broad gauge track, that means the formula is being decided as 0.04% and the degree of curvature is 3 and the ruling gradient which is being provided is 1 in 200. So, what is going to be the compensation here? The compensation is in terms of 0.04% multiplied with the degree of curve. So, 0.04 into 3, the 3 is the degree being given here, multiplied with this, then what we get is 0.12%, and this 0.12% in the compensation which is to be done. The gradient which has been given is 1 in 200, it means 0.5% of the gradient is there. This is 0.5%. So, compensated gradient is going to be 0.5% minus 0.12 is 0.38%, or it will be 1 in 263. It means the gradient has to be eased out from 1 in 200. So, it was 200 here and then 1 was there. Now, what is to be done is that this 1 has to be there in this 263 meters. So, that is a easing out which has been provided at this point. So, with this we close this lecture. What we have discussed is the resistances which are offered due to curvature, due to the starting and acceleration of the locomotives, and the effect of the wind on the locomotive and the train, which comes it in terms of the sectional area. And another thing which we have discussed is the compensation of the gradient, because there is a overlapping of the curvature at that particular point. With this we close it. Thank you, and we will be meeting in the next lecture now.